Good evening, everyone, and welcome to the RSES Manufacturer Webinar Series. I'm Lori Schiavo, RSES Journal Publisher Editor, and I would like to welcome everyone to tonight's session on Advanced Copper Alloys and On-Site Joining Methods for HVAC Systems, presented by John Hipchen. Before we get started, I want to thank the Copper Development Association for sponsoring tonight's webinar. Their generous support is how we keep webinars free for members, and we value their shared commitment to educating HVAC professionals. John's presentation will last approximately 45 minutes. Afterwards, there will be a Q&A session, and Andy Coretta Jr. from the Copper Development Association will be joining the conversation. Please submit any questions you have throughout the presentation using the GoToWebinar dialog box, which is on the right-hand side of your screen. I'll field the questions and ask them aloud to John and Andy. Tonight's presentation is being recorded and will be available online for viewing at your convenience as soon as possible. And now I'd like to introduce our presenter for the evening, John Hipchen.
Hello, everyone. Thank you, Lori, for the introduction. Once again, my name is John Hipchen, and I'll be presenting this webinar today. On behalf of the Copper Development Association, I'd like to welcome everyone. You know, when it comes to transferring heat and moving all types of liquids and gases, copper alloys have been the material of choice for a long, long time. But over the years, our requirements in all industries have changed dramatically. Our focus today, especially in air conditioning and refrigeration, is on energy efficiency and the environment.
John, I'm going to interrupt you really quick.
Well,
I'm not presently seeing your screen. Do you want me to take it back momentarily? Oh, there we go. You're good.
You got it?
Yep. I'm sorry to interrupt.
No problem. Thank you. So as I was saying, our focus today, especially in air conditioning and refrigeration, is on energy efficiency and the environment. And the technology behind copper alloys and copper components has continued to advance and evolve to meet these new requirements. As the title suggests, this webinar is meant as an update on materials and joining methods. And over the next hour, we're going to review some basic practices and properties of copper tube and fittings, but we're also going to discuss some newer advancements that might help solve some of the challenges that you see in the field today. I'm having trouble. I'm sorry, moving to the next slide.
That's okay. You want to get it out of presentation mode for a moment, or hit your space bar?
Yeah, hit what box, Lori? I'm sorry.
Your space bar usually advances your PowerPoint.
All right.
Nope. There you
Got
go.
it. Okay. Before we continue, I want to say a few words about the resources that are available from the Copper Development Association, who, as Lori mentioned, is sponsoring this webinar. The Copper Development Association is the North American arm of the global copper industry, and they're recognized worldwide as the foremost resource on copper and copper alloy applications. And CDA facilitates collaboration between world copper producers, copper product fabricators, and key decision makers in the global market. As happens in any modern industry, questions and challenges come up as a result of new industry-wide requirements and goals. Well, the Copper Development Association answers those challenges by developing and sharing meaningful, credible, and scientifically sound knowledge related to copper products. CDA supports and promotes technologies, systems, applications and solutions in which copper materials play a role. They also develop and maintain teams of highly talented, dedicated, and professional individuals that are committed to promoting the successful use and application of copper materials. And the Copper Development Association works hard to promote sustainability and to encourage responsible environmental practices. We'll start our discussion with a look at the advantages of copper alloy components in HVACR applications, and then we'll turn our attention to copper tubes. We'll review some of the basics about copper alloys, and we'll also go over recommended practices for brazing. We want to spend some time talking about press connect fittings for high pressure air conditioning and refrigeration applications, and then discuss the trend towards smaller diameter tubes in evaporator and condenser coils. There are new developments that we'll discuss related to coils and also to copper tube and fittings. And then finally, a few closing comments, and we'll take some questions. Copper alloys have been used in heat transfer applications for well over 100 years. And the reasons behind that long and successful history are things that field service engineers see firsthand all the time. Even in the highly competitive world that we live in today, copper still represents a very economical solution because it's so easy to work with. Because it can be formed and joined in a short period of time, installations are fast and efficient, and also effective. Copper components are reliable and callbacks are rare. In the field, the excellent workability of copper products allows for fast, strong, leak-free joints. In areas where the use of a flame is prohibited, there is effective joining methods that do not require a torch. And in stark contrast to other materials, copper components can be repaired in the field easily. Copper alloys are inherently resistant to corrosion. Certain alloys are resistant to the presence of organic acids, and copper tubes made from these alloys are specifically being marketed for air conditioning and refrigeration applications, such as evaporator coils. The thermal conductivity of copper is more than 60% higher than aluminum and about 30 times that of stainless steel. Copper alloys are also quite strong. Because of this high strength, copper tubes are able to handle high pressures with relatively thin walls compared to other materials. We'll talk more about new refrigerants and higher operating pressures, but the strength of copper alloys is one of the qualities that's proving to be important to a future of more environmentally friendly refrigerants. Because copper tube can be formed to follow the contour of structures and corners, the numbers of joints and elbows can be minimized, and that results in a savings of material and time. Copper is safe. It does not burn, and it will not carry fire through walls, floors, and ceilings. There are no volatile compounds needed for installation. It doesn't degrade into toxic compounds, and there are effective joining methods that do not require a flame, even for high-pressure applications. Copper tube and fittings are manufactured to well-defined standards and marked with permanent identification, so you know exactly what it is and who made it. It's accepted by virtually every major mechanical code. Finally, no copper used in a building today should ever end up in a landfill. Copper stands alone as an engineering material that can be recycled over and over without degrading its content or properties. So once again, there are good reasons why copper has been used in heat transfer for over 100 years. Copper tube and fittings for air conditioning and refrigeration applications are made from nearly pure copper. It's an alloy we refer to as C122, and it has over 99.9% copper with very small amounts of phosphorus. Copper tube is available in coils or in straight lengths. And if you're working with a coil, it's annealed or soft drawn. But if you're working with straight lengths, it could be annealed or drawn. A drawn tube means it was once at a larger diameter, and through a drawing process that involves a die, the final diameter was reached. This means the copper was cold worked, resulting in a harder material. Annealed tube means the material has undergone a heating process that resulted in a soft temper. This tube is more pliable and easy to form. Strength, formability, and other mechanical factors determine the type of copper tube that will be used in a particular application. For air conditioning and refrigeration, type ACR tube is most common. It meets ASTM specification B280. It is color-coded blue and has a wall thickness that's most like type L B88 tube. Coiled or annealed tube is available in diameters from 3/8 of an inch up to 1 5/8 inches OD. In straight lengths, drawn tube or hard temper is available in diameters from 3/8 all the way to 4 1/8 inches OD. Copper tube can be plastic coated for what we call aggressive or corrosive environments. The tube can also be insulated or even pre-charged. An experienced technician that's been on the job for a while has no doubt noticed an evolution in refrigerants. And the trend with new refrigerants is higher operating pressures. About 25 years ago, government regulations became a factor in the design of air conditioning and refrigeration equipment when the Montreal Protocol took effect. The Montreal Protocol mandated a phase-out plan for CFCs, which are chlorofluorocarbon refrigerants. This covered refrigerants like R12 that are no longer used. HCFC refrigerants, or hydrochlorofluorocarbons, were allowed as transitional replacements until HFC refrigerants were fully implemented. And HFC stands for hydrofluorocarbon, and this family of refrigerants does not have chlorine. And chlorine, in fact, was the problem element, which has been linked to the depletion of the ozone layer. So R22 was a transitional HCFC refrigerant, and today we see this being replaced by HFCs like 134A, 404A, 410A, and a whole host of others. It's typical for HFC refrigerants to operate at higher pressures. Looking forward, we see a push for natural refrigerants such as R744, which is CO2, and R290, which is propane. And refrigerant systems that use CO2 have yet even higher operating pressures. Copper tubes and fittings are well suited for new refrigerants with higher operating pressures. ACR tube is rated to 700 psi at 250 degrees Fahrenheit, and this is certified by UL 207. But manufacturers are actively promoting new products for high pressures. And we'll talk a little bit later about copper tube for extra high pressure applications. When I spoke about the dependability of copper products, I mentioned that copper tube and fittings are manufactured to well-defined standards and marked with permanent identification, so you know exactly what it is and who made it. And here is an example. We can see that this fitting is manufactured for working pressures up to 700 psi. Here is another example of cast copper alloy pressure ratings and manufacturer's identification. Wrought copper fittings, they look exactly like copper tube, is what's preferred for air conditioning and refrigeration brazing, and they're available over a wide range of sizes and types. The exceptional formability of copper gives us the ability to form it at the job site. When tube is bent correctly, it will not collapse on the outside of the bend, and it will not buckle on the inside of the bend either. We've learned from burst testing that the strength of a bent copper tube can actually be greater than it was before bending. Both a annealed tube and drawn tube can be bent with benders. The proper size bender must be used for each size tube. Referring to the copper tube handbook, you can find a table there that provides typical bend dimensions for various diameter tubes. So this slide illustrates the procedure for bending copper tube with a lever-type hand bender. First, with the handles at 180 degrees and the tube holding clip raised out of the way, the tube is inserted in the groove of the forming wheel. Next, the tube holding clip is moved over the tube and the handle is positioned at a right angle. This engages the forming shoe over the tube. At this point, the zero mark on the forming wheel should be even with the front edge of the forming shoe. Looking at the bottom left, the bend is made by pulling the handles toward each other in a smooth, continuous motion. The calibrations on the forming wheel show the angle of the bend. Finally, the bent tube is removed by pivoting the handle to a right angle with the tube and disengaging the forming shoe. And then we release the tube holding clip. So the tool that I'm showing here is just one of many. We're going to turn our attention now to joining methods, and we're going to start with brazing. Brazing is most common in air conditioning and refrigeration applications, and that's for good reasons. It's a fast process. It makes a strong, leak-free joint. Compared to solder, brazing is done at much higher temperatures. Brazing requires filler metals and capillary fittings. And when brazing copper tube to wrought copper fittings, it does not require flux because the phosphorus in the filler metal does that job. However, when other metals are brazed, fluxes are typically required, and it's critical that the correct flux is used. Looking at filler metals, there's two basic types normally used in air conditioning and refrigeration applications. There is a brazing copper phosphorus, or B-cup series, and a brazing silver, or bag series. The B-cup series is most commonly used for air conditioning and refrigeration installations, and these filler metals have higher melting temperatures than the silver-containing bag series. There's a B-cup 2 filler that's recommended for close tolerances. There's B-cup 3, 4, and 5 that are recommended for joints where close tolerances cannot be held. Looking at the composition of B-cup filler alloys, there's phosphorus in amounts that vary from about 4 to 7.5%. The phosphorus in this alloy acts as a fluxing agent. So, when joining copper to copper using a B-cup brazed filler, there is no need for a separate fluxing operation. The filler metals that contain silver, the bag series, are used to join dissimilar metals. These brazed fillers can contain a considerable amount of silver, making them rather expensive in comparison to the B-cup fillers. Note that the bag fillers do not contain phosphorus or any other metal that would act as a fluxing agent. Therefore, a separate fluxing operation is required when you're working with bag brazed fillers. The American Welding Society, or AWS, has developed what they call the 3T rule. It says that if the brazed alloy can penetrate the joint a distance of 3 times the thickness of the thinnest material, which is most often the tube, then the finished brazed joint will be stronger than the tube or the fitting. So the message from the American Welding Society is to shoot for deep penetration of the brazed alloy. And the technique used to heat the joint during the brazing process will be an important factor in achieving that penetration of brazed alloy. A continuous fillet of filler metal should be visible completely around the joint, as illustrated here. The photo on the left shows how the fillet covers the heat-affected zone from the brazing process. In the photo on the right, we see a joint without a fillet and a fracture just outside of the joint. And that fracture is in the exact location where the fillet would normally be to strengthen this area. It's highly recommended for air conditioning and refrigeration installations that the tube be purged with an inert gas during the brazing process. Nitrogen is typically used as the purge gas, and it displaces oxygen from the interior of the system while it's being subjected to the high temperatures of brazing. This eliminates the possibility of forming oxides on the inside surface of the tube. It certainly makes a noticeable difference, as we can see in the cross sections on the slide. Here are 6 installation steps that will ensure an effective brazed joint: measure, cut, ream, clean, flux, and heat. All of these steps are important. The tube must fit all the way into the base of the fitting cup, so measuring the tube is critical. The tube must be cut so it's perpendicular to the tube run, and then any burrs must be removed. Dirt, oil, and oxides that form on the surface of all metals will interfere with the flow of molten brazed alloy, and this flow of alloy is absolutely essential to the quality of the finished brazed joint. Oxides must be removed from the outside of the tube and the inside of the fitting. If flux is required, it's applied to the clean tube and fittings before the assembly is heated to braze temperature. When the joint is assembled, the tube should be inserted hard against the stop of the socket. And it's also important to support the assembly while it's being brazed. This will keep the joint in proper alignment. So we'll look at heating next. We want to apply heat to the parts to be joined with an oxy-fuel or an air-fuel torch. The photo on this slide shows an oxy-fuel torch. You want to adjust the oxygen flow to a neutral flame. A neutral flame has a minimal glow near the nozzle, as the photo shows. The Copper Development Association recommends avoiding a carburizing flame because of the excessive amounts of carbon that this flame introduces into the joint. Excessive oxygen is also a problem, and this flame is referred to as an oxidizing flame. Needless to say, an oxidizing flame should not be used for brazing. Air fuel is sometimes used on smaller joints. Remember, again, to use a neutral flame. The tube should be heated first, beginning about 1 inch from the edge of the fitting and sweeping the flame across the tube in short strokes. The flame should be at right angles to the tube. It's really important that the flame be in motion and not remain on any one point for too long. Even though copper melts at high temperatures, nearly twice the melting point of aluminum, for example, too much heat in one spot for too long can be enough to damage the tube. So after heating the tube, switch the flame to the fitting at the base of the cup. Sweep the flame from the fitting to the tube to get uniform heating. As the fitting comes up to temperature, start sweeping the flame back and forth along the axis of the joint to maintain heat in all the parts to be joined. Remember to keep the flame moving to avoid damaging the tube or the fitting. If cast fittings are used, exercise caution to avoid excessive heating that might crack the fitting. When the tube and fitting assembly has reached the braze temperature, the flame should be angled toward the tube. And now this assembly is ready for braze alloy. So we now have the joint heated and the flame at the base of the fitting angled toward the tube. The filler metal is added at the bottom where the tube enters the socket of the fitting. Heat and capillary action will draw molten alloy into the joint from bottom to top. It's a good idea to keep the flame away from the filler metal itself as it's fed into the joint. The temperature of the tube and fitting at the joint should be high enough to melt the filler metal. As the filler metal is drawn into the joint, we want to keep both the fitting and tube heated by moving the flame back and forth from one to the other. The heating procedure we just reviewed is a proven method, but technicians often develop their own best practices. But do keep the 3T rule in mind and be aware of the problems that can develop from poor brazing. And remember that the continuous fillet of filler metal should be visible completely around the joint, and this fillet is key to an effective and durable braze connection. There's a couple of ways to make joints without using a flame. One way is to create an electric field around the area to be brazed. The inductive energy heats up the metals, resulting in a brazed joint just like we've been looking at. And except for the flame heating techniques, all the guidelines we just discussed apply. In these photos, we see induction brazing being done both on a joint in the field and in the coil manufacturing process on a return bend. Another way to join tubes without using a flame is press connect joints. And this is an area where new advancements in technology, specifically in O-ring materials and tools, has led to press connect joints for high pressure applications like air conditioning and refrigeration. And again, referring to the new refrigerants and higher operating pressures, there seems to be a heightened interest lately in press connect joints. High pressure press connect technology is rated for pressures up to 700 psi at 300 degrees Fahrenheit. What makes high pressure press connect joints different from low pressure are the special jaws and fittings, plus the double 360-degree crimps that can be seen in the photo. As with any air conditioning or refrigeration system, cleanliness is important. The preparation procedure for press connect joints includes removing burrs and chamfering the cut end of the tubes. Make sure that the gasket is in place inside the fitting, and be sure to mark the insertion depth on the tube. Proper sized jaws must be used for the diameter of the tube that you're working with. The tube must be inserted completely into the fitting, and this is where the insertion mark on the tube will provide an easy check that the tube is, in fact, inserted completely. The next steps are to properly place the pressing jaws on the fitting and start the pressing cycle. As this slide shows, the pressing jaw should be centered on the tube and placed over the bead on the fitting. A trigger starts the pressing cycle. It's important when the pressing is complete to make sure the tube has remained fully inserted. And again, the insertion mark that we put on the tube at the beginning of the process will tell us that the tube stayed where it belongs. A go, no-go gauge can check the press connect joints to verify that they were all completed correctly. The go, no-go gauge is always included in the press connect kit, and it has gauges for various tube diameters. When a joint is uncrimped or crimped incorrectly, it will show up on the gauge as we see in the photo on the right. In the photo at the bottom, we see a correctly crimped joint verified by the gauge. To summarize this discussion on press connect joints, This process has two primary advantages over brazing: no flames or a need for purging, and shorter installation times. As fast as brazing is, press connect joints can often be done faster. The time savings increases with larger size tubes and fittings. A third-party comparison of on-site brazing to press connect joints has shown the installation time for press connect to be lower by some 31% for quarter-inch size fittings and 77% for 1 1/8 inch fittings. So again, the advantage for press connect increases with the size of the fittings. Press connect joints are approved for a large number of refrigerants, and as the technology continues to improve, we expect the list of approved refrigerants to grow as well. So we're going to switch gears now and take a look at a new trend in air conditioning and refrigeration coils. When installing coils in the field, you may have noticed a trend toward lighter coils with smaller diameter tubes. And this is a result of the industry focus on energy efficiency. Engineers that design coils have found significant gains in heat transfer by using smaller diameter tubes. And there's an economic advantage to this too. Smaller tubes also mean less material, and less material means lower cost. Although it will take a larger quantity of small diameter tubes to move a particular amount of refrigerant, smaller diameter tubes can handle that pressure with thinner tube walls. And it's surprising what a difference small diameter tubes can make in the amount of material and even the overall size of the coil. Many coils have been redesigned from using 3/8 inch or 9.5 millimeter tubes down to just 1/4 inch or even smaller diameters such as 5 millimeters. The copper industry gave this trend towards small diameter tubes the name microgroove. And micro refers to small diameters, and groove refers to the enhancements that are on the inside of the tube to help improve heat transfer rate. The image on this slide illustrates this trend towards small diameter tubes and coils. This is taken directly from a promotional piece, and the difference in tube diameters between the old and new coils are easy to see. And this manufacturer is pointing out that the refrigerant in the new design has 35% more passes than the older design that had larger tubes. You might notice the spacing of the tubes in the new design. You can see how the air passing through this coil is going to hit more surface area than the older design. And this additional surface area is a large factor in the increased efficiency. Specifically, we're talking about an increase in surface area to volume ratio. For coil manufacturers and their customers, this equates to energy efficiency, mainly moving more heat in a given area with less material and less refrigerant. These coils are very dependable, and small diameter tubes give the heat transfer engineers more options too. These coils can be manufactured with the same proven process that's used for larger diameter tubes. But there's a new manufacturing technology just introduced that's particularly well suited for small diameter copper tubes, and it accelerates the coil manufacturing process significantly. For field service technicians, we're dealing with lighter, more compact coils. We see higher SEER ratings, new refrigerants, and as we've discussed, along with new refrigerants comes higher operating pressures. So let's take a closer look at exactly what makes these coils more efficient. Whenever fluid moves through a tube, the fluid closest to the tube wall behaves differently than the fluid in the center of the tube. The fluid that's right next to the tube wall sets up a boundary layer where heat transfer becomes more difficult. And this applies to the hydraulic motion of fluid as well as the way heat moves from the center of the tube to the tube wall. So heat transfer engineers talk about both hydraulic and thermal boundary layers. So to simplify this a bit, fluid closest to the tubes tends to move slower than the fluid in the center. And even in turbulent flow, a laminar sublayer forms and heat moves slower through these boundary layers than it does in the faster moving fluid toward the center of the tube. Boundary layers act as an insulator and they interfere with the heat transfer that we want. Now the internal enhancements in microgroove tubes, in other words, the grooves and patterns that tube manufacturers put on the inside tube wall, they reduce this boundary layer and they increase heat transfer through the tube wall. You can see the boundary layer in a smooth tube develop and it does not dissipate or go away. But in a tube with microgroove enhancements, the boundary breaks down as it moves over the grooves. Then there's additional mixing of refrigerant that occurs inside the tube because of these grooves, and that also increases the amount of refrigerant that comes in contact with the tube wall. All of this improves the transfer of heat through the tube wall. Airflow goes around the tubes as it passes through a coil, and as it does, the airstream is broken up and heat's transferred into the air. The number of tubes and the location of the tubes has an impact on heat transfer. It also has an impact on the air pressure as it's lost going through the coil. So air forms the same type of boundary layers as refrigerant does, and in many respects, air can be dealt with the same as any fluid. Just as we saw with microgrooves inside of the tubes, outside, the tubes break up any boundary layers that the air tends to form as it flows through the coil. The more tubes we use, the more we break up the boundary layer on the air side, and the more heat transfer we'll get. But in many cases, more tubes also means a higher air side pressure drop. So there's a balance at some point where a coil uses an optimal amount of air to achieve the heat transfer that the system requires. Remember also that heat's being dissipated by the fins, and the fins have slots or louvers, again to break up boundary layers and improve heat transfer. When round copper tube flat thin coils are manufactured, the tubes are expanded. This fastens the tubes to the fins and also makes sure there's sufficient contact to ensure the transfer of heat from inside the tubes into the fins and finally into the air. This has been a mechanical process for many years. A rod, or what's referred to as a bullet, is physically forced through the tube. The bullet is a bit larger in diameter than the tube, and the expansion of about 10% or so does the job. With a trend towards smaller diameter tubes, this process has certainly been doable, but it's become a more delicate and slightly longer process than it is for larger diameter tubes. Very recently, a major equipment manufacturer that builds coil manufacturing systems for most of the world's coil suppliers has introduced a new pressure expansion process. You can see that the conventional mechanical expander requires significant vertical height as well as floor space. The new pressure expander has a smaller footprint and can produce coils much faster than the mechanical process. And because the pressure expansion of copper is extremely consistent and controllable, this process is especially well suited for copper tube coils. This pressure expansion process has been in development for many years, and now that it's introduced, it represents a potentially dramatic shift back to copper tube flat thin coils. For coil manufacturers, this means no more rods or bullets and much faster production times. Faster production times coupled with a huge reduction in scrap rate, that all translates to lower costs for the coil manufacturers. And since there's nothing mechanical touching the inside surface of the tubes, it means that those enhancements inside the tube are untouched and we get their full potential to aid in heat transfer. For field service professionals, we're expecting to see lower cost coils for both indoor and outdoor units. It also means a consistent, easy-to-repair metal throughout the entire system. As this manufacturing advantage is implemented in the coil building industry and it makes its way to the field, we expect the result will be a new interest in copper tube coils. Definitely something that field service professionals should be aware of. So let's turn our attention now to a copper alloy, alloy C194, that's now being used to produce tube for extra high pressure applications. If we look at the composition, that 2 to 2.5% of iron in this alloy is really what gives it the strength to handle working pressures of over 1700 psi. And that pressure rating is UL certified. Also note that the pressure rating does cover brazing and its annealing effect. So if you plan to braze this tube, you don't have to reduce the pressure rating by some 29% like you would for conventional ACR tube. This alloy has excellent brazing properties, and it allows the exact same brazing process to be used that's used for ACR tube. But specific braze alloys are recommended for this extra high pressure tube. What's important for field service technicians about this extra high pressure tube is that this tube will handle the pressure of a CO2 system. And we know that we'll be seeing more and more green natural refrigerants such as CO2 and propane, as well as other high pressure refrigerant systems. So as we conclude, I want to mention how versatile copper really is. There's some 800 different copper alloys that we know of. And throughout history, copper has played a key role in the advancement of our civilization. It always impresses me that as we continue to raise the bar, copper alloys continue to meet the challenge. In the air conditioning and refrigeration industry, copper has traditionally been the material. And certainly there have been alternatives. But as we move into a future where we focus our attention on efficiency and the environment, it seems that copper is again stepping up to the challenge and delivering new levels of performance. Remember that copper in any heat transfer application is an economical solution. It has excellent workability, and in the field, it can be easily joined and repaired. Copper has excellent corrosion resistance, and those properties are being improved all the time with the use of different alloys. No other material has the thermal conductivity of copper for the same price. Copper alloys are strong, they're easy to form, and copper is safe. Copper components have a long and successful history, especially in air conditioning and refrigeration. And when it comes to the environment and sustainability, it's hard to match copper being 100% recyclable. So you can find a wealth of information, including technical data and installation procedures, at our website, copper.org. So I want to thank everyone for attending this webinar, and I also want to thank RSES Magazine and the Copper Development Association for giving me this opportunity to present this material. And I would suggest that you keep an eye out for more webinars in the future that zero in on some of the more broad topics that we discussed today. So I think at this point we are ready to take some questions. I'll turn it back to Lori.
Okay, fantastic. I will leave your slide up as it is right now. We had a question come in quite early. It said, although I have yet to see a copper microchannel condenser, my concern would be of dissimilar metals, especially in Florida. Even 8 miles inland, I have seen very bad corrosion. I guess that wasn't really a question, it was more a comment, but would you like to address that?
Andy, would you like to take a stab at that?
Yeah, I wouldn't expect galvanic corrosion, dissimilar metal corrosion, to impact copper in a copper aluminum system. Galvanic or dissimilar metal corrosion the material that's affected is based on where it stands on the electromotive force series. And when you put copper and aluminum together, aluminum is the more anodic or active metal. Copper is the more cathodic or noble metal, less active metal. And when in a galvanic series, when you put those two, you put two materials together, the anodic metal is the one that corrodes. So in a copper aluminum system, where you would see corrosion in that case would be on the aluminum fins, not on the copper tube that would degrade the copper surface or cause copper failure or coil failure.
Okay. Another question is, are these methods approved for food grade and medical gas piping systems?
Yes, they are definitely for medical gas systems. Andy, did you want to comment on that some more?
Yeah, the copper tube that's used for ACR systems, HVAC systems, ACR copper tube is most often double marked so that we can supply one tube for ACR systems to the ASTM B280 spec, and that same tube for medical gas systems to the B819 specification. The real difference between the two is the sizing convention. ACR tube is sized by outside diameter, where medical gas tube is sized by nominal diameter. And to relate the two, nominal diameter, the OD of a nominal diameter size tube is 1/8 of an inch larger than the nominal size. So a 1-inch med gas tube has a 1 1/8 OD, the same thing as a 1 1/8 OD ACR tube. So the tube themselves are identical, the cleaning processes are identical, and the end result and the cleanliness in the tube is identical. So most often those tubes are dual marked, so you can use them for either system.
Okay. When heating up the tube, do you have suggestions about how one knows that it is heated enough to proceed to the joint?
I'll take this one, John. Yeah, if you notice the photos that John showed in his slides, where he had the torch on the tube, at about 700 to 800 degrees Fahrenheit, the phosphorus in the tube and the fitting itself, remember he said in C122 alloy there's up to 0.04% phosphorus. The phosphorus starts to act as a fluxing agent, and the tube will go from a dark color to a bright, shiny copper color. That tells us that the tube has reached about 800 degrees Fahrenheit and you're approaching brazing temperature. That's the time that you can start testing the brazing alloy to see if it melts. The only thing that really tells you when it's actually at brazing temperature is when the brazing alloy begins to melt. Most brazing alloys used for these copper systems will melt at around 1,000 to 1,100 degrees, 1,200 degrees. So you use that color change to indicate it's about time for the alloy to melt, and then you just test the brazing alloy. When it starts to melt, it's time to make the joint.
Fantastic. There's a lot of technical questions coming in, so get ready, Andy. If a press connect joint fails the gauge, which I'm assuming was the gauge you mentioned testing, will it have to be cut out, or can you press it again?
You can actually press it again. I don't recall. I'd have to look at the manufacturer instructions on how many times you can attempt that. But you can reinsert it into the press jaws, press it again due to the great formability of copper, and repress that joint.
Okay, what are your thoughts on formicary corrosion issues?
What are my thoughts on formicary corrosion? Formicary corrosion does occur. It is not, there's a lot of thoughts on what can make it occur. One, we believe the formicary corrosion issues are likely, they're more publicized than they actually occur. But what we've seen is that an increase in the tightness of construction and lower air changes within a building allow chemicals, formaldehydes, VOCs from building materials to collect on the evaporator coil. and these are thought to cause the formicary corrosion issues that we see. There are a number of manufacturers out there that have introduced solutions to this, such as tin-coated copper tube with aluminum fins, or another copper alloy. Like John said, there's over 800 copper alloys out there. A copper alloy called C422 that has been modified, that stands up extremely well to formicary and other types of corrosion, has similar heat transfer to the C122 alloy, and can be brazed and joined in a similar manner.
Yeah, we're really worried about organic gases when we're talking about this subject. As Andy mentioned, that form from new construction materials. Over time, they dissipate and the condition disappears. But as Andy mentioned, there's different ways, from alloys to coatings, to protect the tube from the organic acids.
Okay. Are there, let's see, I apologize. Are there press fittings available for soft tubing?
No, I don't believe so. That's a great question, and I should know that off the top of my head, but let me look here a second. I believe they're only, the ones for the high pressure system are only used with hard temper tube. We can verify that and include that information. Well, I guess, Lori, is there some way we can get the answer and include that information to the attendees?
Absolutely. I will flag that one as one you'll address offline.
Okay.
Okay. Let's see. With the copper iron alloy C19400, will it be more expensive, and will I be able to mix fittings?
To get the pressure rating, the reason that you would use the C194 or the European equivalent alloy is to get higher pressure ratings. It is a more expensive material, but to maintain that pressure rating, you would get fittings that are made of the same material. So the companies that are out there in the marketplace selling that extra high pressure material also have fittings to go along with it.
And the test data that I've seen on the brazed joints with the extra high pressure tube, those failures were far exceeded the I think far exceeded the burst pressure of the tube. They were really high.
Okay.
Correct.
Okay, the next question is, will copper tubing take the place of stainless steel piping for the condenser in a CO2 transcritical system? I think he meant transcritical.
Will it take the place?
Yeah.
That's yet to be seen in the market. The introduction of the extra high pressure materials, the C194 copper iron materials, is intended to be used in those systems and potentially displace stainless steel because it can handle the pressure, has a higher heat transfer, coefficient heat transfer, and better heat exchange. So it overall is a much better application, or much better material for that heat transfer application.
Okay. Do I need to do anything design-wise exchanging a standard coil to a volume-sized microchannel coil regarding gas and fluid velocities or volumetric compensation to dampen fluid shock?
That's you, John.
Can you read that one more time?
I sure can. Do I need to do anything design-wise exchanging a standard coil to a volume-sized microchannel coil regarding gas and fluid velocities or volumetric compensation to dampen fluid shock?
First
First
of all, they're asking about a microchannel.
You're going to coil manufacturers that replace coils. you're going to have to check closely with the manufacturer to make sure that the ratings for the new coil are going to be appropriate and match up to the older coil. The newer coils, as I mentioned, they can transfer a lot more heat in a smaller area, and you can use that advantage in a couple of ways. One of them is, if you're going to transfer the same amount of heat in that same area, then you can take advantage of higher airflow because of the better heat transfer capability. So there's an awful lot going on there, and I would suggest pretty close contact with the coil manufacturer and check the ratings of that replacement coil and make sure that it's correct. And I don't know that I can address, I think there was the last part of that question had to do with fluid shock. And I can tell you that usually when you go to smaller diameter tubes, there's an increase in the refrigerant side pressure drop, but that they usually get around that by using more circuits in that coil design. So once again, the best way I can answer that would be to go back to the coil manufacturer and make sure all those ratings are going to match up well with the coil that existed in there before.
Okay, I think we have time for a couple more here. Another question, what brazing alloys will be used for the new high copper containing iron?
It's the same brazing alloys that you can use for C122 alloy can also be used for the copper iron alloys. The copper iron alloy, there's a lot of information on the slide, also contains the same amount of phosphorus in the base metals as was in the C122 alloy, making it very brazeable. And the B-cup and bag alloys can still be used. The B-cup alloy can be used with those materials without a flux, much like with the C122 materials. The bag alloys would need the use of a flux.
Okay. Is swaging still recommended for small diameter copper?
I didn't hear what that is. What?
Is swaging still recommended for small diameter copper?
Yes, you can still swage it. You can.
Did we lose you, Andy? Are you still there? I apologize.
Yes, I'm here.
Okay.
Can you hear me?
I hear you now. All right. Give me 1 second as I go through. There seems to be a huge misunderstanding regarding microtube between copper and aluminum. Why is that?
They're actually two different technologies. Copper microgroove, as John talked about in this webinar, is round copper, small diameter round copper tube with an internally enhanced surface. Aluminum microchannel are flat passageways, very small diameter passageways with many small passageways in the surface. And there's performance difference between the two. Small diameter round tubes with enhanced surface doesn't suffer, the coils don't suffer from the problem of refrigerant distribution and tube dry out that you can get in microchannel coils, because it's hard to distribute, evenly distribute refrigerant amongst those very small microchannel passageways. But they're two different technologies. The copper microgroove is actually a tube, microchannel is not, and it's an extruded passage.
And the aluminum microchannel tube is a flat ribbon-shaped tube, and the air is going through fins in between those flat tubes. And what you have with the small diameter copper tubes, it seems that coil engineers are able to use the geometry of placing those tubes and different geometries to play around with getting more heat transfer and breaking up those boundary layers I talked about as the air goes through the coil.
Okay, I'm going to squeeze one more in. We're at time, but I think this will probably be a quick one. Can copper iron alloy be flared?
Copper iron alloys, I'd have to check with the manufacturer. They are harder materials. They're higher strength, harder materials. So they are more difficult to bend and physically manipulate by flaring or swaging or things like that. So they're fairly new to the market. So I can't give you a positive answer on that. But you should be able to do it. I'm not sure if you can do it with the standard flaring tools that we would use right now. It's going to take a higher strength tool most likely.
Okay, well, there's several questions we did not get to, which I will be sure to get to both of you after the webinar. And if anybody else has any questions, you can email webinars@rses.org, and I will be sure to forward them on as well. But I'm going to go ahead and take over now, gentlemen, if you don't mind.
That's all you.
All right. All right. Thank you, everyone, for attending this webinar. And, of course, thank you to John for taking the time to present the topic. Thanks to Andy for assisting with these questions. And thanks to the Copper Development Association for sponsoring the webinar. For those of you who would like to view this presentation at a later date, you can do so in the next few days on the members-only section of rses.org, which I will show you how to get to right now. So you just log in, enter your username and password. Yeah, of course. Let's try that again. Sorry, everybody. A little technical difficulty. Okay, and under the logout button here, you're going to select this My RSES homepage, and then the webinars link here in the left-hand column. And you will see the upcoming webinars that we have scheduled, and the archived ones will appear below this line here. Also, so you know, the webinar attendees from tonight's live event, you will receive a certificate for completing 1 hour of continuing education within 7 to 10 business days. If you have any questions, again, you can email me at webinars@rses.org. Again, that's webinars@rses.org. And thank you again, everyone. Those were great questions. This was a great presentation. Have a great night. This webinar is now concluded.